last one was less than a decade ago. Before then, the most recent occurrence was in 1882. And the next time, it'll be 2117, when few, if any of us, will be alive to see it. Among the most rare and predictable celestial events, the sight of the planet Venus slowly trekking across the face of the sun has been witnessed by humans only 53 times since 2000 years BC. What about the heavens have these phenomena taught us? And what else might we discover about our place in the universe during these next 6+ hours? The Venus Transit 2012, next on NASA television.
Almost 4 hours into our 2012 Venus Transit, you're looking at a live picture, a live feed from Norway. Cameras there of the Venus Transit. You can see, of course, that dot across the sun, the face of the sun. And we've got about 2 hours and 45 minutes left. But for now, let's come back here. Al Feinberg, NASA TV. Dwayne Brown, our Science Mission Directorate Lead Public Affairs Officer in the Office of Communications. And with us, our Planetary Division Director for NASA, Dr. Jim Green. We've got a lot of cool stuff to show you. In the next few minutes, we're going to go halfway around the world in a couple of minutes. But first, we're going to go over to our media maven, our social media maven, Mr. Jason Townsend, who's got some really cool stuff to show us. Jason?
Hi, everybody. How's everybody doing? We're more than halfway through now at this point, and we've got a couple of things that we wanted to share with you. First up, if you're following at NASA_SDO, the Solar Dynamics Observatory, they are releasing images up there. We've just got the latest one coming in, which shows it about halfway through. If then we are also getting some video in from SDO, and this is really, really cool stuff. I mean, this is some awesome video. If we can roll on the video here, it's available on YouTube. We've tweeted it out. It's on at NASA. Here it is, and you can see the Venus is coming into the sun here for ingress. It's going to cut away here in just a second to a much wider shot, so you can see the half the sun there, and then
so cool.
It's going to finish with the full disk here and so on. So it's absolutely wonderful, wonderful video coming in from the Solar Dynamics Observatory. Other thing that we've got going on here, we've got new images that people are uploading to our Flickr group. So if you're taking photos out there, make sure to share them on Flickr. If you search on Flickr for the group Venus Transit, you can put your images up there. Here's a couple of the ones that we've got from that group. First up, if we can get it here, first up we've got a wonderful picture of the sun with Venus just beginning to appear there with a little bit of cloudiness. The next one we've got going on here is a wonderful, wonderful zoomed in view here that another user took on Flickr. And then our final shot here is a different way of looking at the sun in that it's being focused onto a piece of paper here, so you're not actually staring at it. Remember, if you're online or you are out looking at the Venus Transit, to make sure you're doing it safely. One of the big questions that we've been having is, where can we just get pictures live of this? So we've got tons of webcams from all over the globe. If you check out venustransit.nasa.gov, you can see all of those that are out there. But make sure you're following along, joining the conversation using the hashtag #VenusTransit. So that's what we've got right now cooking on social media. Follow along with us on @NASA, NASA on Facebook, and NASA on Google+. And we're going to turn it back over to these guys now.
Thank you, Jason. And gentlemen, we are now going to go halfway around the world, actually the other side of the world, where it is probably close to 1 or 2 o'clock tomorrow afternoon in Alice Springs, Northern Territory, Australia. Is Michael Johnson there? Good day, mate.
7 minutes. Hey, I'll do.
Well, we see the kids there with the flag.
Make sure they know we're on.
Communications being what they are.
I can just get the head angle.
The weather looks very nice out there, Al.
Those kids are from the Centralian Middle School in Alice Springs.
Welcome from Australia. We're here. It's now almost 11:30. We've just gone past the midpoint of the transit here. I'm in beautiful Alice Springs, Australia, here in the Northern Territory. Behind me, I have students from Centralian Middle School who have been hosting us all week for activities. Say hi, guys.
Hi! My name's Bill.
There's Bill and Bob. Hey, we picked Australia here for two reasons. The first one is that we can actually see the entire transit. The second one was because of the weather. It is absolutely gorgeous right now weather. It's towards their southern winter. The temperature's perfect, except this morning we had clouds. So if you were watching our feed a little bit this morning, you saw a little bit of clouds, but there is just a few clouds in the sky, and we are set up for an absolutely gorgeous first and second contact. Want to let you know that we have been working with students all week. We've been teaching them lessons. We've been talking about what is a transit. We've been showing them how to, a little bit about the parallax angle. So let me tell you a little bit about that now. If you know that we actually measured the distance to the sun by using a parallax angle. So we have two different positions that were on our expedition. We have one in the Gobi Desert and one here in Australia with these guys. Say hi again. Hi! See with these guys here. If you go ahead and take your thumb and place it out to an object far away and cover it, close one eye and cover it, and then blink back and forth, you'll notice that your thumb will actually move position to where you can actually see the object. Well, knowing that distance there, we can actually do some trigonometry and find out the distance to the sun from the Earth. Now, that's already been done before, so why do we want to redo it again? Well, what's the best part of science? Replicating our data, making sure that everything we do is consistently correct. Because if we find something wrong this time, which I don't think we will, but hey, there may be something different. We're looking, our cameras right now, if you see this telescope, is actually a calcium telescope. So it's looking at the sun in the element of calcium in the scope. What's really interesting is I don't know what's going to happen at third and fourth contact with that atmosphere. Some of you were watching before and you saw with the nice hydrogen alpha, you saw the atmosphere of Venus reflecting around, and you saw the black drop effect. Well, that was all in kind of what's called a hydrogen alpha. So it's looking at hydrogen. This one's looking at calcium. And since we missed it this morning, I don't know what's going to happen with that black drop effect with that. I'm hoping it's all the same. It may be cooler. I don't know. That's the mystery of science. Say hi again.
Hi! I'm Bill. John.
So
I'm Bill.
again, we're here at Alice Springs. Check out our website for our other streams. You can see live images at www.ccsse.org. Stay tuned here on this webcast for updates and things I'll come up to. Take a look at some of the other sites. When you look at the other sites, look at something in particular. Look at where the sun is, or where Venus is crossing the sun in each one. I bet you it's a little bit different. Also look at the time. We're planning on it. Our egress starts about 1:57 here in Alice Springs. In other places, it actually happens a little bit later. Well, when you think of why it does that, well, it's because we're looking from all different angles. And again, those angles are how we measure those distances.
Ready to wrap.
All right. I'm glad you guys have joined us from Alice Springs. One more time, say bye for everybody. Bye! Don't forget, we're from the www.ccsfc.org. Let us know how you like our feed. And you have a great day.
Michael Johnson from the Coca-Cola Space Science Center, Columbus State University in Georgia, with the Centralian Middle School students in Alice Springs, Northern Territory, Australia. Great time down there. The weather was nice.
A lot of fun. We're joined again, as we said earlier, with Jim Green. But I want to send a shout out to all the NASA centers who have been participating, holding events, and clearly this thing and this event is worldwide, but our NASA centers across the country, and there are all kinds of things going on. They're doing some great things, and if you guys are listening out there, and I'm sure you are, great job, and we still have a lot more to go before we end out. Jim, a couple of things on what people are seeing. We in the previous segment, we saw the little black dot. Explain to folks, because when the telescopes look at the sun, it's like flipped, or there's something going on there where the dot should be here, but it's there. Explain what's going on in that situation.
Well, telescopes are a little bit different than binoculars. You know, with binoculars, you can look through them and everything looks right. It just looks magnified. But with telescopes, they actually flip things. And that's why Venus, as it entered the disk, wasn't exactly where everyone thought it was. In addition to that, as telescopes are also rigged up with cameras and other types of feeds, and they have a certain orientation, and they track the sun across the sky, then they're not actually looking at the sun and its rotational axis. So sometimes north and south on the sun wouldn't exactly be north and south as you see it. So when you look at the Venus transit, you have to really compare it to things like what SDO is observing and posting. That's all been rectified, and it looks beautiful. You can also look at the set of sunspots. The sunspots, because we're going up to solar maximum, increase, and there's typically a line of those sunspots at a certain latitude, both in the northern and southern hemisphere. And as you get down to solar maximum, the latitude of those sunspots get closer and closer to about 20 or 15 degrees latitude on the sun. And so consequently, you don't really see sunspots along the equator. So you add all those things up, and you can actually tell and predict the orientation of the sun. You can see how the optical systems have flipped it, and then you can say, okay, Venus is going to go from one side to another, and then watch it over time, and indeed that confirms actually what's going on with those particular images.
Jim, let's go right now to this image, which is correct, if I am correct. This is our first look at Mount Wilson, from Mount Wilson Observatory in California, in the Angeles National Forest in California. 60-inch telescope, and this is the Venus Transit 2012 live from that perspective.
We see some sunspots over to the right.
There's sunspots way over to the right. But what you notice more than anything else is a lot of the atmospheric turbulence. Okay, so this must be late in the day. So we must be seeing the rising air currents. That's moving up in our view, and consequently it changes the index of refraction. But all it does really is move those images around a little bit. So we don't really see a very crisp, nice, beautiful black dot that Venus would be, nor do we see exactly the sunspots the way they would appear. They don't really move like that.
Now, does that affect our gathering of scientific data?
Yes, actually it does. It changes our timing a little bit. That's why one of the reasons why we do want to observe it off this planet. And in fact, Don Pettit is in the space station observing it now. And so he won't have any of the atmospheric effects that we have on the ground. Now, what we've been doing is accumulating a lot of these images, many of that we possibly can, on our website, venustransit.nasa.gov. And what we'd like to do over time is be able to use that data that's come in from many different sources. Now, yeah, that's a beautiful one.
That's from SDO.
See, that's just beautiful. It's very close to white light, meaning how you would observe it if you were at the right location at the moment, seeing this. But what's really spectacular about this one, though it's very simple, you see the beautiful Venus, which has really looked like it's carved out the light from the sun. It's really blocked it well. But then compare that against the sunspots. You see the dark area, that's called the umbra of the sunspot, and then around that is the penumbra. and that is not quite as dark, and that tells you this. That gives you a great idea what the structure of the sunspots are.
Now, how big would that sunspot be?
Well, if you took the Earth and you actually moved it all the way to the sun, yes, any one of those little bitty sunspots off to the side would be about the size of the Earth.
Really? So that larger one there?
Oh, that's enormous. That's much bigger than the Earth. And in fact, we're coming towards solar maximum now. So we would expect to see more and more magnetic activity. We would expect to see bigger and larger sunspots. And about every other cycle, some of these sunspots get to be so enormous that they could rival the size of that projected image of Venus on the sun. And those are just enormous. And that's why when you have the glasses, even though you may use these during Venus transit, you can use these anytime. So you could really look at the sun, particularly around solar maximum, and you might be able to see sunspots nearly the size of the projected image of Venus that we see here now.
And to keep things in perspective, literally, Venus is not nearly as big in actuality as those sunspots.
Oh yeah, Venus is itty bitty compared to those. If you move Venus all the way to the sun, now Venus is like 2/3 of an astronomical unit. You know, we're 1 AU away, that's 93 million miles. Venus is more like 67 million miles away from the sun. So if you moved Venus to the sun, it would shrink and shrink and shrink, and it become about the size of one of those little bitty dots that are associated with that bigger sunspot.
Here we're back at Mount Wilson with a wide shot. You can see everybody with their telescopes out there.
They are. They're enjoying that view.
I wonder if we can put on our glasses now. Would we see anything?
It'd be pretty dark. They're designed to be that way, by the way, because the sun is indeed quite intense. It's one of the reasons why you don't even want to look at it with your naked eye. Sometimes late in the day, you know, where there's a lot of smog, you might look and you know, see the sun. But in reality, you should avoid doing that. It can be harmful to your eyesight.
And Jim, take us back a little bit, a little history lesson here.
Sure.
Being head of the Planetary Division and the year of the solar system, but you guys have been studying Venus for many years. Can you give us a quick snapshot of the first mission to Venus to the present and what we've learned?
Yeah, I'll be delighted to. In fact, you know, at the dawn of the space age, right after Sputnik, you know, this nation in the Soviet Union decided they were also going to trek out into the solar system. And so we had planned and launched 4 lunar probes, lunar rangers, 1, 2, 3, and 4, by 1962. Every one of them failed. By 1962, we also launched a mission called Mariner 1 to Venus. That failed. But Mariner 2, launched in August 1962, nearly 50 years ago, was successful.
And Jim, let me jump in here. Don't hold that story, but we just got some breaking news.
Oh,
we got an image from the International Space
Station.
Oh,
wonderful. Don's coming through.
Don Pettit, well-known science geek, right?
Yes, he is.
And all the most positive way of putting that. He is... this is crew sleep, as we mentioned earlier, but Don's not sleeping because Don is so excited about this.
Hey, that's great.
Maybe he heard that science never sleeps, right?
Yeah, I bet he did. I bet he has.
Jason, did you have something else for us?
Yeah, if you guys want to go and check it out, you can hop on to the @NASA Twitter feed. You can hop on to NASA Facebook or NASA on Google+. We've just shared the link on Flickr where you can go and get all of the different images that Don Pettit has now put up from the International Space Station. And as they keep coming in, we'll make sure that we keep getting them out there and sharing them so you guys can join the conversation. Just follow #VenusTransit. So.
Thanks, Jason. Okay, so Dr. Green, we wanted to get that station, but give us a quick, again, continue on the history lesson on Venus.
50 years ago, Mariner 2 was successful, flew by Venus, and really gave us a great view of it. It told us that the clouds were really impenetrable. We couldn't see down to the ground of Venus from the Earth, and we couldn't do that from Mariner 2. So that then launched a whole series of other scientific investigations. And nearly 20 missions have been launched to Venus over these last 50 years, many of them unsuccessful. Venus turns out to be a hard object to really get to know. But fortunately, what's happened is many Russian missions were very successful. Venera 13 and 14 actually landed on the surface. And as Lika mentioned earlier today, the surface temperature of Venus is hot enough to melt lead. The pressure is 90 times that of our own atmosphere. You have to go way deep into the ocean to get that same pressure. And so these bathtub-like battleships landing down on the surface of Venus actually only survived for about an hour and 20 minutes. But they gave us a fantastic view of what that atmospheric profile was all about, and temperature and density all the way down to the ground. Now, in addition to that, the Russians launched very successfully several more missions, most notably Vega 1 and 2. And Vega actually launched balloons into the atmosphere of Venus. And you watched from ground the balloons in that upper atmosphere, and they lasted until they went around in the super rotation of the wind speed. In fact, the wind speed at the top of the clouds of Venus is in 4 days can actually transit the planet. So that's running at an average about 250 miles per hour. So we're talking about hurricane winds like you can't imagine, force 10 or something. I don't know what it would be on the scale. But and so those balloons made atmospheric measurements and did wonderful. But it really took the U.S. mission called Magellan to be able to have a ground-penetrating radar after it got in orbit to penetrate those clouds and really globally map what the surface of Venus looked like.
And what year was that?
That was in the 80s. Sorry, yes, late 80s. Mm-hmm. And so what happened is we found well over 1,000 volcanoes. We recognized how volcanic the surface is. In fact, we believe Venus is so volcanic that it actually resurfaces itself every 900 million years. So since its beginning, it may have done that several times.
Not a place you want to take a family vacation to, I guess.
It's a pretty tough environment. In fact, some of these volcanoes are as high as our own Mount Everest. Wow. And so that's just been a spectacular part. Also mentioned is there's a layer of sulfuric acid. It's at about 60 kilometers up. And that layer of sulfuric acid actually forms little raindrops. And they begin to drop as they condense around dust and then end up actually evaporating as they get down into the higher temperature atmosphere and form this circulation pattern.
And we got another picture here to show you, and then we're going to bump out and come back at 12:30.
And you're going to join us, Jim?
Absolutely.
This is Norway. Is that right? We're going to show you Norway on the way out, and we'll be back at 12:30. Jim will be here. Dwayne, of course, and myself, Al Feinberg.
And Jason.
And Jason Townsend. So back to NASA Edge right after this.
The future astronomical public will not be satisfied unless all practical use is made of the transits of Venus of 1874 and 1882.
distance to the sun. There were several methods for doing it, but they did depend both on the timing of the contacts and on the measurement of Venus when it was actually on the face of the sun. So you needed to measure it for very precise, that's why it's black light. Just if you wanted to measure when that contact was, you know, if you put your two things together very closely, you only see that the to go together before you actually have it. And that's what happened with the sun. So if it's actually contact, then you're in trouble because that's not accuracy.
Education and outreach are a big part of the Venus Transit this year, and right now we're about to go to school with two seniors. We have Camila Fishtaller from Northern Virginia, Yorktown High School, and Carol Mayo from Juniata College in Pennsylvania. First, Camila, tell us a little bit about the transit and give us an introduction about how the
Venus is running on the black line all around Earth, and she has
She's got it. Yeah, baby, she's got it. Well, I'm your Venus. I'm your fire at your desire. Well, I'm your Venus. I'm your fire at your desire.
cross.
Okay.
And so that's why this is slightly tilted.
Oh, I see. So the tilt is for Venus's orbit.
Yes.
Okay.
And there's a reason why we don't see a transit every
Complete the cycle. How
years because of the tilt. So half of Venus's orbit is above Earth's orbit and half is below Earth's orbit. So 2 points are too high above the sun's disk to be seen, and 2 points are too low on Earth's disk to be seen.
Wow. Okay. My brain just folded, but it could be altitude. Now, Franklin, you have any questions about this?
I was right under the chair when you fall.
No. Okay. So one question I have right off the bat is you've got this letter system A, B, C, D, and E, right?
Yes.
So when they complete the cycle, how many years would that represent total when they do one full rotation?
Like when they meet back?
Yeah.
Okay, so that would be 8 years for Earth and 13 years for Venus, or Venus years.
Okay, so now is that why we talked about earlier why we have two Venus transits? Like in 2004, that would have been down here, right?
Yeah.
And then 2012.
No.
Or I'm sorry. Okay. Yeah, see. This is why we do these activities.
Okay, so this kind of goes into the next point.
Okay. Okay. Yeah. Sorry. I'll step back.
Venus is actually moving slightly faster than 8/13 of an Earth year.
Okay.
So actually, we say this pentagon, the the corners of the pentagon are where the Venus passes Earth, so they match up.
Okay.
If we were to turn it slightly, it turns very, very slowly. So
Part of this that brings to light some of the years that are involved in this, right? Do you have another?
And then the next 8 years, it's kind of a little past the line.
Yes.
And
With the numbers and dates on it.
it's over there.
Oh, all right. See, yeah.
5.5 years is because the points had to align again back at that point.
Wow. Okay. Now the 100 years is starting to make a little more.
It would be this part. So that's, and then every 1/3, 3/5